Hello again. Welcome to the second lecture about body structures. This one, Body Structures 2, will be a focus on the lab exercises. My name is R.Whitehead. I'm a professor of architecture at Iowa State University, where I teach structures and design there. I've written a book called Structures by Design, Thinking, Making, Breaking. If you haven't seen it, make sure you look at Body Structures Part 1, in which we talk about how the main reason for being able to use our bodies, how our bodies help us to visualize important structural behavior and stresses and forces. And in that one, we go through a lot of real basic information about what are forces, how do we diagram them, how do we get equilibrium, what are the states of stress. It's all pretty important stuff to know. In this one, we're really going to try to talk through this idea of the fun times and serious business of architectural structures. And I mean, what's going on here is obviously hilarious and spectacular. And yet, what are we taking from it? Like, what could we learn from the idea of how they've configured themselves? How everybody in here is working, the stresses that you see on their bodies and their hands. What can we actually tell from that might actually help inform us of what this means for architecture? So, as a reminder, the reason that we use our bodies for structures, anyways, is because it's already a system that we understand well. If you look at any of these enactments over here on the side, you can see a whole series of different ways that we interact with the world on a daily basis, in which we actually can figure out relatively complex structural behaviors that we have to take part in, but we do so without, first applying math. Now, it's important that we have that as an intuitive shared experience, but we need to be able to extract that experience out to be able to visualize it and show it. So, the part of this lab, the reminder here is to record your experiment. We rarely take notes about how we feel when we walk, or walk carrying a briefcase, or walk carrying books. Second, think about equilibrium and the states of equilibrium. Again, as we're climbing stairs or holding on to a child, we really don't think too much about it. We just make sure that we maintain that equilibrium. The other thing is to think about the stress types, what we're feeling when this actually happens to us. So the lab I'm going to show you then follows one of the very first lectures in the structural sequence here. This is our way of just trying to say, okay, now that we've understood what forces, loads, equilibrium, etc. are, somewhat in the abstract based on the lecture, we immediately then go and we have a lab. In this lab, and you can see some of the write-up here, we have two basic challenges. One challenge, how high can you reach using only your body as a structure? And challenge number two, how far can you span? It's important that you articulate what are the goals of this? What are you actually trying to achieve? What are the objectives? So that when students see it more than just having fun, they see the serious business then of what you're trying to achieve, what they're looking for when they enact. So to recap the lab before we even begin, there's a couple basic elements of knowledge that need to be understood. First, there's an inescapable relationship between a structural form and type, location, and magnitude of the stresses. These were the states of stress that we discussed in the previous lecture: compression, tension, torsion and shear, and bending. And in this, you can see, of course, how these different states of stress relate to the different configurations of the body. So the reason we want to start here again is because that's the whole point of enacting things with our body, is that we can then work backwards from that and say, how did this form introduce a particular type of stress? The other thing to recap before you begin has to do with equilibrium. Equilibrium, and in this case, understanding how these body structures might fail. Now, equilibrium, as a reminder, is it's the sum of all the forces, and we want those to equal zero. So the vertical, horizontal, and rotational. We want to have a static body. We don't want it moving up and down, side to side, or rotating. Now, there's two different ways in which this failure may occur. It may happen with external conditions, in which a support no longer holds, or internal, when the body or the structure itself is no longer able to maintain that equilibrium and push up against those forces. Again, external in terms of rotation, where they're not in balance, or internal, where there's an element that can't keep it in rotational equilibrium. Also, as a reminder before you even begin, about the force arrows. Using force arrows is essential to actually be able to map out what we're trying to do here. Arrow length equals force magnitude. The angle is the direction, and the sense is whether it's pointing to or away from a particular point, so that we know what stresses it induces upon that. The other thing to remember, of course, is that forces aren't just up and down, that forces can have be resultant forces that are diagonal, and as such, they have both vertical and horizontal force components. So even if your body is at a particular angle, you can still sort of square off that overall geometry to be able to find both horizontal and vertical force components to it. And of course, before you begin, a reminder about the scientific method. If we only treat this like how far can you span and how high can you reach, and we just go out there and do stuff with our bodies, we're forgetting this really important idea is like, how do we learn from what it is that we did? The scientific method here, that there's an experiment question, in this case, how far can you span, how high can you reach? There has to be an informed hypothesis, and ideally this is then based on the skills and knowledge that are already taught in the lecture. What do we anticipate about equilibrium and forces, etc., right? Well, let's try to act out this scenario. So then there's a test, and this is a controlled test, meaning like actually write down what it is that you think you're going to do it, take pictures of it, measure it, etc., and then findings. And the findings is really an important part that sometimes is overlooked in this lab. Sometimes it's like, oh, wow, that was really hard. Oh, boy, that didn't go very well. What do you mean? How so? And definitely have someone designated for each lab team that is able to write down these feelings. Oh, it hurt there, or it fell apart at that moment. And of course, you want to really record all this information qualitatively and quantitatively. Take pictures, have a tape measure, measure it, talk before, talk during, and talk after. Therefore, you can then analyze and report on this. And when you analyze and report on it, then you can go back and, if needed to, go back to that experimental question. Now, on to the lab. Challenge number 1, how high can you reach? One of the first lessons that you find out has to do with this combined loads and support. We know that if there's this basic state of translational equilibrium, the ground is supporting the person. But when we start to have more people stacked up or more elements stacked up, there is a force flow, the 20 to the 100 to the 200, right? And all that works just fine, but we find out right away that it can't be reversed, right? We would know right away that the cat would be in some trouble here. This is important because it's not just about can you support the weight above. It also has to do with where the actual force flow is actually happening throughout a more complex system. When you can really start to be able to map something like that out, so it isn't just one arrow and then one arrow supporting, but actually thinking through how that works its way across, then it really helps to be able to visualize what it is that you've made with your body. When you get taller, there's challenges that happen with stability. So as a theoretical demonstration, let's just say that there were 6 people that were all stacked up. And so even if the weight could be supported by the bottom person, and probably not, we know that that's not at all the biggest threat to this particular enactment. It's way too easy to tip over. So what we learn right away is that there's challenges with stability that has to do with geometry. This is a very, very quick exercise that you can do before they even start building up higher. First, have a person stand there, have one person within this particular plane push them. They're able to push them out of the plane because they're not geometrically stabilized. Then ask the second person to stabilize themselves within that plane. They generally do so by triangulating it with their legs. The triangle, in other words, creates stability. Same thing this way. Push, push forward, stabilize with the leg out. So you can think about that when you are trying to get a stable connection, you want to think about triangulating this. So the support conditions, in other words, the legs and feet, etc., can and should be, of course, altered to provide this type of stability. And think about and ask them to resist within the plane in which that force would be applied. So getting the form right makes everything easier. As you build up, if one were to, and again, I'm not endorsing this for a lab exercise, but a more of a theoretical exercise, as you go higher, the base gets wider. There's a way of locking arms together, and then making it circular. It avoids having a weak axis. It makes a circular axis all the way around. The lowest weight higher up. And then as this comes down, there's a resistance to this buckling that comes down below. All this weight eventually is going to have an outward dynamic force. So they're pushing and supporting to make sure that that outward thrust doesn't come through. Interesting part about this when we start to think about stability and geometry is how it's analogous then to tall and thin forces of buildings. And we covered this in the very first lecture about body structures, but a way of thinking about Gothic churches, and the taller and higher it gets, thrust comes out. In order to avoid that thrust, there's another body there, and then theoretically we'd have another body there. So Lesson 4, when we start to get taller, there's also these challenges with sequencing. When you think about how people get into these poses that are shown, not only do we know that being taller needs to be wider, but how does it get to be this way? And so then the sequencing of it is really a function of our bodies not being really pretty terrible at this stuff because they aren't rigid. And so trying to find balance and equilibrium in these is actually quite difficult to do. And normally it requires a lot more people than actually are there in the final pose. And you can see that really well articulated here in this particular photo. So think about this from the perspective of resources. Our bodies are sort of props of what it takes to actually get in this final pose. It's a really interesting way of thinking about how larger buildings can be built and what it takes to build them. When you're trying to hold up something higher, think again about how arrows and geometry can really help analyze the difference between legs that are straight, legs that are off at an angle. And in this case, in lecture 1, we looked at the idea of being able to map that, and how if the vertical stays consistent between both of these two scenarios, that the diagonal clearly has more force, and so there's more force in the leg and less potentially stable overall geometry. When you put it all together, a very simple pose actually has some pretty profound lessons here. We know that there's a series of combined loads, holding it high above the head, triangulating that, comes through, down, transfers over and through. The force flow of it, the force flow of course makes some sense. I appreciate how this is being held really close to their bodies so that the force coming here doesn't have far to transfer to go down into those particular legs. The geometry for stability, triangle, triangle, and of course the overall form of all of them is a triangle as well. You can also see that they are turned inwards, and turning inwards allows it to be triangulated in the opposite direction too. So the first one is, let's say, the x-axis, and there's a triangle in the x-axis, but then the support is also triangulated in the y-axis as well. Then the other one is the sneaky sort of lesson about connections here. Obviously, there's a risk of the person on top falling forward or falling backwards. And one way to try to make sure that that doesn't happen is to try to fix this connection as much as possible. So you can see that the positioning of the hands helps to try to make that a right angle. And it's also held close to the body here as well, so that also helps secure it in that location. Challenge number 2, how far can you span? The first lesson here is just asking them to act something out individually. And if they try to hold a weight outwards from their body and just say, well, how far can you hold this out? It helps to define a couple different terms. What does span mean? What does the overall reach of this mean? And why is that important? What you find out right away is that they obviously understand through lived experience that equilibrium and geometry and stability all go together. The leg is sort of kicked out to help balance the center of gravity to keep it above the point of support of the foot. So the further out one reaches, if there's not a counterweight back here, there's a tendency to tip over. Now, this is one where you take a picture of it and you really want to measure it to be able to see, all right, what is that span from the center of that theoretical center of the support? One could also say, from the main point of support, how far does it reach on either side? As they go to figure out how far they can span individually, my main recommendation is that they enact all 4 of these poses right away. In doing all 4 of these poses, it's immediately going to lock into place this question of how far can you span and what type of stress happens within one's body. The form of the spanning body and the types of stresses that are involved are inextricable. So let's go down below. A compression form. This then is one point of support and a second point of support, and in order to be fully compressed, right, it's a relatively limited amount of span. But it's relatively easy to hold this pose too because it's in compression. A tension-based pose, where if that's one point of support and the hands are another point of support is about the same as the compression one. In this one, it lengthens the abdomen and tenses the overall body. If it was more of a plank position here, and whether that has to do with the one on the far right where the hands are out, ankles are down, we know that the overall span then is between the toes and the hands. That's the span. And we also know that this is a pretty hard pose to hold for quite a while. We know that there's compression in the top and tension at the bottom. And if you were to take this pose and then shift it to the side and only be up on one arm, again, we have a relatively similar, well, we have the same span as the bending span, but we have two more forces that are also happening here. A really high level of shear that's happening in the shoulder where it wants to slip past, and torsion where the body wants to rotate through. Things really get interesting when you start to have multiple people involved, because intuitively right away there's a couple poses that people drop into. The idea to point out here is just to let these poses occur and just to try to ask students to figure out why it is that they chose those particular forms. When they go to group exercises, it's also important to help visualize the internal stresses that are happening. The one where both the bodies are leaning out here, we know that there's tension in the arms, that the bodies in fact are compressed. We have a certain amount of reach. The thrust from one side and the other side cancels them out. Or if they actually turn it and they want to make an arch, we know that there's compression in the arms, and in fact the bodies are also compressed. And what gets relatively difficult about making this span farther and farther is that eventually the thrust at the base makes it so that they slip, and the center of gravity, of course, tilts over. So pay attention to what are the types of stresses in the arms. As they're doing it, ask, well, how do you feel? Where do you feel it? What stresses occur in the center person's body? And then look at the connections of their feet. Always think about how the forces are resolved when you have something that wants to sort of turn over. Also pay attention to the sequencing of it. How does this stay in equilibrium in both translational and rotational equilibrium? And they've sort of intuitively balanced their overall weight. So a certain portion of Michael's arm actually balances this whole thing out, and that he's shifted his center of gravity over by rotating. As we start to evaluate the choices that we make about structural efficiency and structural form, it is important also to think about the amount of resources that it takes to get there. So how much farther does this actually span for the amount of extra resources it took to do so? Which one of these poses is harder and why? No, we have a spine, right? We have hips. We're not a rigid body. In order to become a rigid body like this, our muscles have to do all the work. In order to get in, because this is a flat body, we know that that is going to be in bending stress. So it's easier then to rely upon our ligaments and our muscles to resist in tension. So as Michael lays out in his intention here, and Dora and Lana both lean backwards, we're able to get full tension, and then they're compressed down. So understanding the bending stress and loading for beams and bodies, which scenario of these below would be hardest to hold and why? So the reason I'm asking the question again is just to revisit this, because we want to try to connect a loading diagram, which of course we always do for buildings to show how forces move through a building, with the concept of bending stress. In all of these, the span length is the same. In this case, there's a relatively large cat that's sitting about mid-span. And so then when there's several small cats that are distributed all the way through. So which ones? How would we know? Again, you know by acting this out. Understanding the bending stress for loading and beams, this has to do with moment forces. And this again was in the lecture 1 about this. Take a body, take a weight, hold that weight a certain distance P out, right? That's your force, and the distance D from the center. As that force gets further and further out, the maximum distance has the highest amount of bending moment. And we know as that gets farther out, we can feel that bending moment as a rotation around the shoulder here. So what? Well, that bending moment is exactly what's happening for a beam when it's in bending. Here we have the person spanning in the plank pose. We know it's compressing and tensed, and we know that there's a desire actually to sort of collapse in doing so. Why? Because within a beam, bending stress in a beam is measured by moment force. You can make this analogy relatively quickly. So then a longer span, further distance between the feet and the hands, we know makes the moment force harder. We also know down here that that maximum moment makes that moment span the highest, right? So this is a very quick way of being able to say the longer the span and the more weight that happens within that span, the more moment stress there's going to be, and therefore the more difficulty bending. This is a huge concept that oftentimes takes semesters of additional instruction to have it come across to students. Lesson 5, when we move to more group settings, the stresses in long span group enactments, these get really tricky and also pretty fun. Definitely use some caution in doing so, but you'll find out that again, it's really difficult to span farther and farther unless we just start to add more and more resources here. One of the main long span enactments was the Firth Bridge. In this one, the person on the top is sitting on top of a ledge held up by cricket bats down below. And now normally they'd want to sort of tilt in and collapse in, but there's a counterweight on the two sides here. And they're showing you that the stability of the triangulation between the arms, right? We got tension arms, compression, sitting on a base, right? Tension, compression. It actually makes for a relatively small amount of span in here. Now, that type of, you could take this structure and ask them to diagram that out, ask them to diagram the stresses that happen within that. The reason they used cricket bats is because they couldn't just rely on hands. Connections and stresses in long span environments, our bodies, of course, fall apart with our feet and our hands. So they're poor substitutes for the rigid bodies that we need to span this long distance. So be aware of the limitations when we do that. As you're getting into these particular things, start to think then about the analogies to other actual building forms. In this one, the way that they're standing back to the side, you have a long span of tension right there, is exactly analogous to the Dulles Airport and the angle of those supporting columns at the Dulles Airport. Or in this case, where they're actually trying to mimic a bicycle wheel, this one at the Expo grounds in Queens, you have a compression ring around the outside and a tension ring in the middle. And the difficulty here is you can't really have a compression ring. They all want to sort of fall inwards, so they're leaning backwards to not fall inwards. And the group in the middle, they couldn't just do it by holding their hands, so they actually had to lock their elbows in place, and that is a direct analogy then to the tension ring. As you go to try to make these body structures, think about how you're going to assess what you're feeling or what information you're trying to get. So one of the critical lessons about the think, make, break process is knowing what information you're hoping to find at each stage. So before you even begin enacting these, think strategically about what you're planning to do and why it might or might not work. Document it, measure, take photographs, right? These are experiments. So because they're experiments, all useful experiments start with a considerate hypotheses. Think, what's going to happen? What do we think is going to happen? Next, go through the entire process of acting this thing out, making the structures with your bodies. You may learn certain strategies from one exercise that helps you in another. As you act them out, be mindful of your posture, the placement of your supports, feet, hands, etc., and the locations inside your body where you feel stresses. High, low, shoulder, wrist, foot, all of that matters because it actually lends a lot of insight into basic foundation structural ideas about stresses and connections and form and force flow. So then when you're doing it, gather objective data by documenting these poses with photos, notes, measurements, use different perspectives so you can see your body as a three-dimensional construct. And then compare how the structure behaves or then breaks with the hypothesis that you had. So to make sure that this act of breaking is productive, be specific about the type of information you're hoping to learn as a result of doing that. When you lift something close in here versus lifting something out, what is it you're trying to learn by that? And then once you sort of feel the difference between, how do you then react? Finally, record your activities in a lab report. Answer specific questions about, this is what I felt, this is what I learned, based on the assigned objectives. In my opinion, there's many types of structural conditions that you'll understand by visualizing them or acting them out using this body structures method. In one class lab, you might be learned about forces, or you'd be able to feel and then understand stresses. You can understand the different types of stresses: compression, tension, bending, torsion, shear. You can understand then how equilibrium happens, where one weight pulls you over too much. You can understand the necessary elements of configuration and how forces move through the body, and even how basic acts of stacking or then spanning with your bodies require a certain level of cunningness and strategy in order to distribute the forces while maintaining equilibrium. Those are huge structural concepts to try to understand, but we know that there's ways that we can do that just by using our bodies. If and when you were lost, and whenever you were trying to understand structures as you get more advanced, think about these basic exercises and what your body can teach you. When you're trying to say, like, what sort of forces move through this, what sort of stresses are happening within there, rely back on the tool and the model that you know the most, which is your body. Body structures in the lessons illuminate the tools we use throughout all of your studies. So for conditions that defy the bounds of your body, you can still use these experiences to understand these internal stresses and the structural behaviors that you learned through these haptic exercises. Learning to translate these exercises and these experiences into free body diagrams of arrows, vectors, etc., is a transitional way to be able to move into documenting structural conditions with measurable and quantifiable numbers, which might allow you to test and calculate these conditions, and therefore, in doing so, improve your structural proposals. Good luck.